Friends, in this session we are going to discuss about the determination of atomic mass by a mass spectrometer, So, yeah, don't worry. I'm sorry for that because kuna kiu sana. So, tuanze kipindi chetu. Mass spectrometer is the device. Mass spectrometer is the device which is used in the determination of atomic mass of elements. Now, in this session, we'll be discussing about how it works, the mechanism of functioning of the mass spectrometer, and every aspect of the mass spectrometer, and all calculations which are involved in mass spectrometry. So, mass spectrometer is used to determine atomic mass and detect presence of isotopes and their abundance. If we remember, we shall see that in the mass spectrometer, finally we come up with the results which, when we plot them in the graph, they are coming like this way. And then in this graph, this is like y and this is like x. In the y-axis, we'll have the relative abundance, percentage abundance. That means abundance ni kwamba hii isotopes imechukua kipande gani. We can regard an element as the piece of this soil. And then, if this is our element, from here, this piece can be occupied in different way. That means, for example, from here to here, it can be one isotope. So let's say this is one isotope, and here is another isotope. So this will be the percentage abundance of the one isotope, and this will be the percentage abundance of another isotope. And even by looking by your naked eyes here, you will see that this is a quarter. That means it is 25%. And this is 3/4. That means 75%. So here, depending on the number of isotopes, we'll have different number of peaks. The number of peaks, peak number 1, peak number 2, peak number 3, peak number 4, determine how many isotopes an element consists of. So this peak may have the mass of, let's say 4, 6, let's say 8, let's say 10. These are just hypothetical masses. Lakini kwenye hizi peak huku chini tunakuwa tuna isotopic mass. So isotopic mass huku percentage abundance. Let's say hapa ni percentage plan. Always the summation of these percentage abundance leads to 0. So always our percentage abundance ambayo inakuwa ni total, it is 0 always. Lakini okay, it is 100. Sorry, it's 100. It's not 0. So I just confused. I just mixed the concept. Always the total percentage abundance, it is 100. It's 100. So tunachosema ni kwamba hii inatoka kwenye mashine inaitwa mass spectrometry. Mass spectrometer. Na method ya kupima inaitwa mass spectrometry. So hii inatoka kwenye mashine. Hii graph inatoka kwenye mashine. Ni mashine inatoa signals zinaenda kwenye detector. Detector unakuja kupata graph kama hii hapa. Kutoka kwenye detector unapata graph kama hii hapa. This is the graph from our detector, how it can be plotted. Now what we are saying ni kwamba determination of atomic mass and isotope abundance by using mass spectrometer is known as mass spectrometry. So mass spectrometry is the technique, or sometimes they call it spectroscopy. Spectroscopy is the technique used for determination of relative atomic masses using mass spectrometer. So mass spectrometer is an instrument. Mass spectrometer is an instrument, and mass spectrometry is the technique used. Mass spectrometry is the technique. So about the uses for mass spectrometer. Uses of mass spectrometer. First is determination of relative atomic mass. Determination of relative atomic mass. Tukipata hizo isotopic mass na zile pale tutapata average atomic mass, ambayo nikwambia the average atomic mass and the relative atomic mass, their value, they are approximately the same. However, it's not the same thing. So average atomic mass and relative atomic mass ni vitu viwili tofauti. Lakini ya pili ni determination of relative molecular mass of a compound. Determination of relative molecular mass of a compound. Kama tuna compound fulani tukiingiza kwenye mass spectrometry, tunaweza tukapata relative molecular mass ya hiyo compound. Ya tatu ni determination of abundance of isotope. Kama tulivyoona kwamba you can calculate the percentage abundance of different isotopes by using mass spectrometry. Lakini toka hapo tuna identification of a compound. So mass spectrometry obtained and information about the peaks, height, and charge to mass ratio of these different isotopes of the compound. They can be fed into the computer, and if you fed them into the computer, you can get the corresponding compound. So the computer compares the spectrum of the unknown compound with those in the data bank and thus identifies the compound. So always in the computer unakuwa umeshaweka spectrum za element mbalimbali na compound mbalimbali. So ukifeed to the spectrum tayari manake computer inasema kwamba this is the spectrum of a certain compound. So unakuwa umeshajua how unakuwa umeshajua hii compound ni compound gani. From there, let's discuss the mass spectrometer itself and how it functions. I can draw the simple diagram representing the mass spectrometer, and in my diagram, I will have this one, and then from here, I will have the ionization chamber here. I will have the ionization chamber. From the ionization chamber, I will have the plates. Here you will have this one, which will go this way, and then you will bend. And then here you will have this one, which also will go this way, and then it will bend. So it will bend like this way. And then from here, we'll have a detector, and then finally we'll have a recorder. So from here, I can draw here the accelerator, and then deflection system consists of electromagnet. Deflection system consists of electromagnet. Deflection system consists of electromagnet. And from here, it's like this way. So the diagram which you'll find in my notes, it is not that much complicated, but also this mass spectrometer can be drawn in different ways. So don't worry, in my notes you'll find the diagram. You may use that. You may use the diagram from other books which you know or which you use. But this is the basic diagram which can represent the mass spectrometer. From here I can draw just I can call this as the heating filament. Heating filament. then I can call here as this is an electromagnet. Here is the detector, and here is the recorder. In the recorder here there are graphs which are drawn of different peaks representing the number of isotopes. Then here we have the route for sample to be inserted. Now I want to explain this mass spectrometry. Always we have a question in this part ambayo huwa wanauliza withdraw na pia uelezee inafanyaje kazi. Withdraw na pia uelezee inafanyaje kazi. Hizi hapa ni accelerating plates. Now when we are discussing about the mass spectrometer, one thing we need to know is that this consists of basically 5 stages. Here tunakuwa tunaingiza gas ya ile sample tunaye identify. So tuna vaporize somewhere, tunachoingiza hapa ni gas, or we are putting vapor. So tukiingiza hii vapor hapa, ikikutana na hot filament, hii vapor ina become ionized. So vapor ikikutana na hot filament ina become ionized. Ikisha become ionized, kumbuka kwamba hizi samples zinakuwa ni za element tofauti. Lakini ikishakuwa ionized, huku kuna plates hapa. Hizi plates zinaivuta ile ionized sample. So hizi hapa tunazita kama ni accelerating plates. Manake hapa tunaingiza sample ambayo iko vaporized. So number 1 we can say it is like a vaporization plus ionization. That is stage number 1. Vaporization, and then after that you are ionizing. Ukishaingiza hapo una-ionize your sample. Lakini number 2 it is acceleration. That means hizi hapa zikishakuwa ionized hapa, lazima kuna kitu kizivute zielekee huko. What pulled them to this direction is electric field which is present in these plates. Kwa kuna electric field, ambayo electric field itazivuta hizi ions zitaenda kwenye this direction. So ions hapa zitapita kwenye stream moja kuja kwenye hii direction. That is acceleration. From there, in the third step, we will have deflection. So in the deflection, here we have the deflection system. What happens in the deflection is that hapa tunakuwa tuna ions nyingi zimekuja, lakini kwa sababu tunataka mwisho wa siku tupate a graph like this with different peaks, and these different peaks, they have different isotopic masses. Remember, the charges in these isotopes, it is the same because they have the same number of electrons. So the charges after ionization will be the same. But one thing you need to note is that these isotopes, they have different masses. The extent of deflection of an isotope depends on its charge to mass ratio. That means tutakuwa tuna heavier na tutakuwa tuna lighter. Kwa mfano, tuseme tuna M1, tuna M2 and M3. Let's take this as an example. And let's say M1 is less than M2 is less than M3. That means M1 is the lighter particle and M3 is the heavier particle. So M1 is the lighter particle, yani particle ambayo ina mass ndogo, na M3 ni particle ambayo ina mass kubwa. Remember I told you kwamba charge inakuwa inafanana. Why charge inafanana? Because isotopes, they have the same atomic number. That means they have the same number of electrons. So kama charge inafanana, this E is constant. The extent of deflection, let me give you a certain formula. The extent of deflection D is directly proportional to charge divided by mass. But from that formula, we have said E is equal to constant. Let's say E is equal to constant K. If E is constant, now we can say that, for example, in this formula, we can say D is equal to constant K, then E divided by M. Removing the proportionality sign, you make a constant K. But from here, ukishakuwa D is equal to K, E, tunasema kwamba since K and E are all constant, all of these they make another constant. Kwa constant huwa zina uwezo wa kulandana, kuvaana. Constant K na E zinatengeneza constant mwingine. So from there, D will be equal to another constant, let's say K will be equal to K divided by M. Ushawasema E imeenda wapi? E bado ipo, ila tu imetengeneza another constant K. From there, if D is equal to constant K divided by M, that means D will be inversely proportional to mass M. That's where I wanted to reach. D is inversely proportional to mass M. And as we know, in the inversely proportional, that when this one increases, this decreases. And when this one increases, this decreases. Now, we have three isotopic masses, M1, M2, and M3. And from here, we say M1 is less than M2 is less than M3. That means huyu hapa M1 atakuwa na masi ndogo. Kama masi ni ndogo, kwenye inversely proportionality, masi ndogo itakuwa na deflection kubwa. That means, let's say hapa tuna deflection tatu. Tukifika kwenye electromagnet, tuna deflection ya kwanza, yule pale. Deflection ya kwanza huyu hapa. Deflection ya pili, let's say ni huyu hapa. Na deflection ya tatu, let's say ni yule pale. Asa unaweza kuona kwamba kuna deflection hizi. Deflection moja amekuwa ni huyu hapa. Deflection ya pili amekuwa ni huyu hapa. Na deflection ya tatu amekuwa ni huyu hapa. Sasa the question come, kati ya wa kwanza, wa pili na watatu, yupi ndo atakuwa na charge to mass ratio ndogo na yupi atakuwa na charge to mass ratio kubwa? Hilo swali ndio tunalijibu hapa, ninalielezea. Ni kwamba mass anapokuwa mdogo, deflection inakuwa kubwa. Deflection inakuwa kubwa maana yake bending. Deflection, that means bending. Kwa sababu hichi kitu kilikuwa kinaenda straight, kikibend maana yake itaenda this way. The extent of bending depends on the mass. Kwa mass ikiwa mdogo, deflection itakuwa kubwa. That means huyo hapa alikuwa ni isotope with smallest mass. Smallest mass. Lakini huyo hapa katikati maana yake ndio alikuwa na mass ya katikati. Na huyo hapa mwenye mass kubwa, deflection itakuwa ndogo. So this will be an isotope with largest mass, or the heavier isotope. That's all about the deflection system. Deflection system include party hii hapa ambayo deflection yake inategemea charge to mass ratio. From there, number 4, we have a detector there. So after deflection, tunaweza tukachange magnetic field in different way to make sure that hizi hapa zinakuja kufika wapi? Hapa kwenye detector. Kwa hiyo tunachange magnetic field tukiona labda magnetic field iko kwa namna ambayo isotope moja ameenda kugonga kule wao. So tunajua okay, magnetic field hii haitoshi kwa hiyo. Tunaongeza magnetic field hiyo hapa iwe deflected more. Unaona? So tunafanya variation ya magnetic field ili kwamba tuna adjust magnetic field ili kwamba isotope zote ziweze kugusa detector. So zikigusa detector, from the detector information itaenda hapo kwenye recorder. So number 4 is detector, and number 5 is recorder. From the recorder here we'll have graphs, kama nilivyosema tutakuwa na graphs hapa. Kwa kwenye recorder hizi graphs tukizichukua tukaziplot zitaonekana kama hivi. Tukizichukua hizo graphs hizi graphs za kwenye recorder tukaziplot zitatengeneza a graph like that one. So you get the notes, and from the notes you see all of these, how the mass spectrometer works. And this one among the commonest question which most of people most of teachers they ask in the exam is about the diffraction system in the mass spectrometer, kwamba ni kwa namna gani ambavyo tunaweza kufanya mass spectrometer hapo na tukapata finally hizo graph. So the height of peaks correspond to relative abundance, while the number of peaks correspond to the number of isotopes. Height of peaks correspond to the relative abundance, and the number of peaks correspond to the relative. From there tuende kuona baadhi ya solid examples ambazo nimekuambia. Hii inaitwa mass spectrometry. And then huyu device inaitwa mass spectrometer. Technique inaitwa mass spectrometry. And then tunakuwa tuna graph inaitwa mass spectrum. Spectrum is this graph, mass spectrum. Device spectrometer. Method spectrometry or spectroscopy method. So tuone examples ambazo tutakuwa tunafanya kupitia data tulizozipata kutoka kwenye huyu mass spectrometer. Data ambazo tutakuwa tumezipata hapa, tuone kwamba kuna calculation gani ambazo zinakuwa zinahusika. So tutasoma hapo maswali mengi tu, mengi tutasolve maswali. So tuone tu maswali hapo. In the notes you find questions. Na kama tulisema kule mwanzoni, AR is calculated as percentage ya isotope kwa kwanza times mass, tunajumlisha percentage ya isotope kwa pili times mass, tunajumlisha percentage ya isotope kwa tatu times mass, then huyo hapa tuna divide by total percent. I hope haya maswali nimeshaifanya form 2, lakini tunarudia tena. So for example, tumepewa the mass spectrum for lead, and I will draw it. So the mass spectrum for lead inakuwa inaonekana kama hivi, and then from here we have this one, we have this one, then from here we have this one, and then we have this one. So here we are given it is 1.5, we are given 23.6, then you are given 23.6, we are given 22.6, and then also we are given 52.3. So it could be best kama hiyo 1.5 ningeweka iwe low kama hivi. So huku tuna percentage abundance, na huku chini tuna 204, toka hapo tuna 206, toka hapo tuna 207, na toka hapo tuna 208. tuna 208. The question is calculate the relative or average atomic mass of lead. Average or relative atomic mass. Nimekwambia hizo terminology huwa always zinakuwa used interchangeably, and because most of our teachers they don't know that they are different, so tutakiwa tuende nao. Average atomic mass AR itakuwa sana percentage ya isotope kwanza mara mass yake. Percentage ya isotope ya kwanza ni 1.5 mara mass yake ambayo ni 204. Tutajumlisha percentage ya isotope ya pili ambayo ni 23.6 mara mass yake ambayo ni 206. Tutajumlisha percentage ya isotope ya tatu ambayo ni 22.6 mara mass yake ambayo ni mass yake ni 207. Then hapa tutajumlisha percentage ya isotope wa mwisho ambayo ni 52.3 times mass yake ambayo ni 108. Tutadivide by total percent. Total percent hapo ni ngapi? Tuone total percent 204 plus 206 plus 207 plus 208. Total percent. Oh, okay. Sorry, nimeadd hizi baada ya kuandisha. 1.5 plus 23.6 plus 22.6 plus 52.3. So total percent hapo tutapata ni 100. So huyo hapo atakuwa ni sana. Uchukue hizo hapo. Let us just solve together with you. So we are starting with 1.5 times 204. So plus 23.6 times 206 plus taenda 22.6 times 207 plus plus ya mwisho ngapi itakuwa ni 52.3 times 208. Tapata hiyo hapo. Then tukidivide kwa 100. Okay. Now this is our correct final answer is relative atomic mass of lead ni hiyo hapo. Lakini from there kuna maswali mengine ambayo unaweza kupewa maelezo, usipewe graphs. So unaweza kupewa maelezo, usipewe graphs. Tumeona kwamba boron is known to have two isotopes whose masses ni 10.016 mass M1 10.106 and I mean 0.16 and 11.013 and M2 11.013 and they exist in the proportion 20 and 8 respectively. So you have an 20%, you have an 8%. Okay, simply average atomic mass itakuwa ni 20 times 10.016 plus 8 times 11.013 divided by 100. Hapo tapata ni 20 times 10.016 plus 8 times 0.13. Hii hapa divided by 100 ni 10.8. Atomic mass of boron is 10.8. So 10.8. Haya, toka hapo a sample funiko was analyzed in mass spectrometer. 3 peaks were observed. Kuna maswali ya group discussion hapa yako, there are many and you can solve them because these questions are common. So utasolve maswali ya group discussion, and after that in the next session we will start discussing with the atomic models. This marks the end of this session. In the next session we'll be discussing with the atomic models.